Hey everyone, I am Miss Hu, your physics teacher. In this video lesson, we are going to go through DC motor. This is a topic in both the SPM and IGCSE physics syllabus, and it follows the concept of a force on a current carrying conductor. So, if you haven't learned about forces on a current carrying conductor yet, and if you don't know how to use Fleming's left hand rule, please watch my video on that lesson first before you come into this lesson, because you need that as a prerequisite to understand this topic. Now, of course, there's always a lot more to know about this topic beyond what I am covering in this video lesson, so please feel free to do your own research, or you can watch my other educational videos. What I'll be covering in this video lesson is just the information that you would need enough to answer the questions in your examinations. So let's get started. So first, let's just go through quickly the concept of the force acting on a current carrying conductor. If we place a wire that has current flowing through it. In this case, this arrow represents the direction of the current. As current flows through this wire, and we place it in a magnetic field. So the magnetic field here is generated between these two permanent magnets. When we place a current carrying wire in the magnetic field, this generates a force that causes the wire to move. Which direction it moves in can be determined using Fleming's left hand rule. So let's recall Fleming's left hand rule. This is force, this is magnet, this is current. So to find the direction of the force, follow the magnetic field here, north to south. Current is flowing that way, and that's why the force is moving downwards, which means that the wire in this case will be moving downwards. So like I said, if you have not learned this or you cannot remember what you've learned, please go watch my video lesson on this topic. For now, we're going to see how this can be made into a suitable application. So instead of having just a single wire, we take this wire and we make it into a loop like this. So this is all part of the same circuit. Now, because this wire is part of the same circuit, obviously the current is also all going to flow in a particular direction. So if we look at the dry cell over here, remember the longer line is a positive terminal of the dry cell, while the shorter line here represents the negative terminal of the dry cell. And current flows from positive to negative, which means that current is flowing in this direction. So I'm going to draw arrows throughout the circuit to show the direction of the current in this circuit. For the forces acting on the wire, we will only focus on the parts of the wire that's actually in the magnetic field. So in this case, these two wires. Now, because these two wires are part of the same circuit, the current direction will be opposite as well. Logical, right? So let's recall what we've just revised in the previous slide. There's a current carrying conductor placed in a magnetic field, and this will generate a force on the wire. Two wires, each of them will experience a force. Different directions, they will experience forces in different directions. Let's look at the wire on the left first. So using Fleming's left-hand rule, so the index finger represents magnetic field. This has to follow north to south, north to south. This is the current, and current is flowing that way. So we're going to get this finger to follow that direction. So north to south, the current is flowing away from you. You can use your hand to follow my hand. You'll find that when you line up this finger and this finger, right? See, you can rotate, but they have to line up. Okay. So you'll find that your thumb points downwards, which means that the force acting on the wire is moving downwards. So obviously, if this was moving down, this has to move in the opposite direction. Obviously, it's going up. So if you want to double check, you can. So we have north to south. Now, the current's coming towards you, and you find that your thumb is pointing up, which means that the force is moving upwards. So what we have here is a pair of wires with current flowing in opposite directions, producing a couple of forces that are in opposite directions. So the term couple that is used in electromagnetism in this case can refer to the pair of forces moving in the opposite direction. So while you always think, oh, couple, yay, pairing, oh, and romantic, romantic. Okay, in this case, the couple here refers to the pair of forces. So yes, the two yellow arrows, you can just say they are a couple. You don't even need to say a couple of forces, you can just call it a couple. So there's a couple acting on this loop of wire. I'm going to put it in yellow just to make it a little bit different. So when you look at what happens here, now remember these two are part of the same loop of wire. So on the same wire, if one side is going down and one side is going up, you're going to find that this causes the wire to rotate. So there will be a rotation, in this case, anti-clockwise direction. So usually to allow the rotation, we place a pivot, like a support, a spoke over here that holds the wires in such a way that it allows the wire loop to continue to rotate. However, if you look at this connection, obviously this connection is not going to allow for continuous rotations. So this is not how we normally would create that device. So to allow for continuous rotation, we need to make some modifications over here. I'm going to duplicate this slide so that you can see how to make this modification. So for this section here, instead of having the wires connect directly to the circuit, we can put something that's circular to allow for the continuous rotation. In this case, we can put a ring. But the problem is you can't put a complete circular ring. Okay, let me fix that drawing. It looks really awful. We can't put a complete circular ring because what happens is that this would cause the current to short circuit it, because direct connection, right? So instead, we're going to split the ring. In this case, for example, two half circles. And each side of the loop is connected to each half circle. So the ring obviously has to be made of a conductive material. The name for these two rings is a commutator or a split ring. So both names are acceptable. Sometimes they even combine it. It's a split ring commutator. So the split ring or commutator or split ring commutator refers to this one ring that has been split into two. To allow for continuous rotation, there must be a continuous connection with the current. So to allow the connection between the commutator and the circuit, the connection is used with carbon brushes. Carbon brushes here. Put it in different colors so that we can see the label. The carbon brushes are this and this. So what happens here is as this loop rotates, the split ring commutator will rotate together, and a connection of current between the loop and the circuit is made with the carbon brushes. So the split over here is to allow the current to be able to change direction every time this loop or wire coil rotates. Because as you can see, as this moves down, the left side will go to the right side and the current direction inside this loop has to change in order to allow for the continuous rotation in the same direction. If you want a clearer picture, here's what I mean. Let's say I label this A, B, C, D. So in this case, you can see that current from the circuit is flowing from A to B to C to D. But when a rotation happens, let's say a half cycle rotation, AB will move to the right, CD will move to the left. So again, just to show you, I'm going to duplicate this one more time. And what we'll find after a half rotation is that there's a change in direction. So now A and B are on the right while C and D are on the left. But we still want the rotation to be in the same direction. You can't have it. That's not, effective or efficient at all. For this, the current still has to flow this way. Okay, just backtrack again. You can see overall that the current is flowing clockwise direction. And in the coil over here, it's A, B, C, D. But once A, B, and C, D have changed positions, we still need the current to flow overall clockwise direction. But the current now is flowing D to C to B to A. So the split ring commutator allows for this change of current direction in the coil in order to maintain the same continuous rotation of the coil. So I'll write that over here with a sticky note. Okay, the function of a commutator or split ring is to allow the current to change direction every half cycle. So this is how you can write in your exams the function of the split ring commutator. Let's make this larger so that you can see it. So the function of this entire contraption is actually to allow for continuous rotation. So by hooking up a wire coil with a split ring and carbon brush to the circuit, we can get a coil that's able to continuously rotate. And this is a DC motor. So basically, if you look at a motor, it's an electrical device that will rotate, right? Where do you find motors? In fans, in vehicles to make the wheels turn and move. So the motor has that continuous rotation, and this setup allows for that continuous rotation. The coil, because it's a moving part of the motor, is also known as the armature. So the armature is normally the moving part of the machine, and because the coil is moving, that's the armature. So this is a DC motor. DC stands for direct current, and it's a DC motor because it uses direct current power supply. Now, do we use AC motors, which are motors which use alternating current? Yes, we do. In fact, a majority of motors out there are alternating current motors, but we don't learn about it at SPM or IGCSE because the construction of an AC motor is a little bit more complex than a DC motor. So good news for you guys, you don't have to learn something so complicated because this is an introduction to the concept of electromagnetism. We only need to learn about DC motors for this particular topic. Here's an excellent animation video which we can find on YouTube that shows a working principle of a DC motor. If you'd like to have the link to this YouTube video, I put it in the description below. This is not my video, so thank you very much to the makers of this YouTube video for this very excellent animation. So you can see here, we have the DC power supply connected to the coil. And this is a simple representation of what the commutator looks like. So we've got the split ring commutator here, which are the copper half circles. And the black color blobs here are actually the carbon brushes. Now, as a coil rotates, can you see that the commutator is rotating together with the coil? The carbon brush stays in place to allow for a continuous connection between the power supply and the coil. I'm going to slow this down. And let's replay that again. So let's replay, and you can see how, as the coil rotates, the commutator rotates together to allow for the connection between the power supply with the coil. So if you want to look at a real-life DC motor, here's a close-up of a small DC motor. As you can see here, to make this more efficient, they don't just use one wire loop. Obviously, that's not very efficient. So they have many loops. This copper strips here, you can see there's gaps. These all make up one commutator. So a commutator doesn't only have to be split into two, it can be split into several pieces as well. Usually it's to reduce friction because when there are gaps, there's less contact friction, but it still allows for continuous connection with the circuit. This will then be in contact with the power supply using a carbon brush. And that's it about DC motors. So if you found this video educational and helpful, please click like and subscribe for more lessons, solutions, and exam strategies from your physics teacher, Miss Hu. Happy studying!